In this diagram that you see before you, we are going to be looking at proton NMR chemical shifts, and then we'll move on to carbon NMR chemical shifts. And then I will proceed to give a fairly lengthy discussion of how to tell the difference between different types of aromatic rings by IR, proton NMR, and carbon NMR with examples. So what we have before you is a chemical shift chart from your book on proton NMR. The scale goes from 0 to 13 parts per million. And the book tells you where different protons are based on shifts, and those are pretty good, but it's a lot of information and it's hard to memorize all of that information. So I'm going to try to make this easier and more of a trend kind of a situation rather than a memorizing situation. The proton's carbon matters a lot. You need to be aware of the hybridization of the carbon that the proton is attached to. If the proton is on an sp3 hybridized carbon, the chemical shift will be something just less than 1 to something greater than 4. And it will be in this region right in here. Now there are 3 regions in this region. We'll talk about that. If the proton is on an sp2 hybridized carbon, the proton usually shows up somewhere between 4.5 to about 10 parts per million. That's typical. And if the proton is on an sp hybridized carbon, the only time that would actually be the case is if it's on a terminal alkyne. It just happens to fall right in the same region as the protons on sp3 hybridized carbons, but they are very rarely encountered. In each of these other 2 regions, the protons on sp3 hybridized carbons and the protons on sp2 hybridized carbons, there are 3 subregions. And the neat thing about this is they follow the exact same trends. So we'll start off with the sp3s. In this region just below 1 to right around 2 parts per million, we find protons on sp3 hybridized carbons that are surrounded by only other carbons and hydrogens. In other words, we're in the alkane region. And that's where you're going to find protons that are literally on an alkane chain part of a molecule. If the proton is on an sp3 hybridized carbon and is adjacent to an sp2 hybridized carbon, be that an allylic system or next to a carbonyl group or next to triple bonds or next to an aromatic ring, I don't care. The point is it's next to a pi bond system because the carbon here is sp2 hybridized. If your proton on your sp3 hybridized carbon is adjacent to a pi bond, it'll show up somewhere around 2 to 2.5. That's a very typical region for something like that. If, on the other hand, your proton shows up on an sp3 hybridized carbon and is adjacent to an electronegative atom like a halogen, oxygen, nitrogen, it typically will show up somewhere between 3 to 4. The more electronegative the atom is, the further down in that direction it will be. Now, occasionally you will see protons out of this region and still be on an sp3 hybridized carbon, but that may be due to the fact that it got double whammied by more than one group. What I mean by that is maybe it's next to an electronegative atom and a ring, or maybe it's next to 2 electronegative atoms. It will get shifted further downfield if there are more than one of these groups attached. In the sp2 region, when we have a proton on an sp2 hybridized carbon, we see very similar trends. If you are a proton on an sp2 hybridized carbon surrounded by only other carbons and hydrogens, you are an alkene, and that will show up in this region of 4.5 to 6.5, just like we saw for the alkanes that were only by other hydrogens and carbons. If, on the other hand, the proton is on an sp2 hybridized carbon that is adjacent to other pi systems, it will be between 6.5 to 8.5 because it's aromatic. That's why it's there. It's adjacent to a pi system, very much like this, only it's starting off on an sp2 hybridized carbon. Just beyond that, between 9 and 10, we find the chemical shift for a proton on an sp2 hybridized carbon adjacent to an electronegative atom. The only one you see in this situation, though, is the aldehyde. But it's very similar to what we saw here. You have a proton on an sp2 hybridized carbon adjacent to an electronegative atom. But you see the same subgroups in the same order when you're talking about proton NMR. We see similar things in carbon NMR. This is a carbon NMR chemical shift diagram, and it goes from 0 to 220. Excuse me. The scale is different, but the trends are exactly the same. In this region, from just a little bit above 0 to usually about 80-ish is where we find our sp3 hybridized carbons. And in this region, from about 110 to about 220 is where we find our sp2 hybridized carbons. And right smack in the same region as our sp3s, we find our sp hybridized carbons. Very similar to what we saw with the proton NMR. In this diagram, there are also 3 subsections. So if we're looking at the sp3 hybridized carbons, in blue here, this region from just above 0 to just maybe around 40 or a little bit above 40, we find protons attached to other hydrogens and carbon atoms. So this would be where we find our alkanes, more than not. If the sp3 hybridized carbon is adjacent to an sp2 hybridized carbon, it happens to fall in the exact same region. You really can't distinguish them in carbon NMR, though they do tend to be a little bit more to the left here, a little bit further downfield, but not always. And then just beyond that, from about mid-40s to about 80 is where you find your sp3 hybridized carbons attached to an electronegative atom, typically oxygen. The others are usually a little bit more in this area, but oxygen does tend to go a little further downfield. But that's where we find our sp3 hybridized carbons. If they are sp2 hybridized carbons, they're going to be down in this region. Our alkenes, which are carbons that are sp2 hybridized attached to other carbons and hydrogens, show up in this region of about 110 to about 160. That's where they show up. And like we saw with the sp3 hybridized carbons, the carbons that are sp2 hybridized and adjacent to pi bonds are in the exact same region. They're on top of each other. So we find our aromatic rings between 110 and 160 as well. Now, if we happen to have an sp2 hybridized carbon with an electronegative atom attached, it tends to be the most downfield, between 160 to 220. And there are a variety of these. But that's where we're looking for chemical shifts. And I will refer to these again if needed, but I would strongly suggest that you print off some of these types of charts and mark them up for yourself as you see here. And as you hopefully can see, we see the same trends regardless of whether it's a proton NMR or a carbon NMR. The trends are exactly the same. Now, I promised that we would look at the rings in terms of IR, carbon NMR, and proton NMR, and what you should be able to discern in terms of the spectra so that you can identify one versus the other. So what I have done here is I've drawn the rings with substituents X and Y. So this one's mono-substituted, ortho-substituted, meta-substituted, and para-substituted. You'll notice with the mono and the para, I've drawn a dotted line so that you can see where the plane of symmetry is in the molecule. I have numbered the carbons that are chemically unique in blue for each of these, and I have put the hydrogens in green so that you can identify them as you look at these structures. In class, I know I mentioned this, but there is a region in the fingerprint region of IR that can be helpful to distinguish these rings from one another. It's not indicative all the way of what ring it is, but it will help you narrow it down. If it's a mono-substituted or a meta-substituted aromatic ring, in this region you will have 2 peaks. The exact number locations are not really important. What's important is that you notice there are 2 peaks in these regions. And for ortho and para, there would only be a single peak in these regions. For carbon NMR, you're always again looking in this region of 110 to 160 for the carbon atoms. For a mono-substituted ring, there is 1, 2, 3, 4 chemically unique carbon atoms, so you're only going to see 4 peaks. Carbon 1, as you can see here, would be a short one, and that's because it doesn't have a hydrogen attached to it. Carbon 4 here would be chemically unique, so it's a medium height sized peak. And carbon 2 has some symmetry, so it's a little taller, as does carbon 3. It's got an equivalent carbon, and so it's also a little taller. So what you're going to see in there are the 4 peaks. 1 will be short, 2 will be tall, and 1 will be of medium height. If you're looking at an ortho substituted ring, there are 6 chemically unique carbons. They're all chemically unique. Carbons 1 and 6 will be short because they don't have hydrogens on them, and carbons 2, 3, 4, and 5 each have a hydrogen on them, so they will be tall peaks. If you're looking at meta-substituted, again, there are 6 chemically unique carbon atoms. Carbons 1 and 5 do not have hydrogens on them, so they will be short. And carbons 2, 3, 4, and 6 do have hydrogens on them, so they will be tall. A para-substituted ring does have a plane of symmetry. As long as X and Y are not the same compound, the same substrate, carbons 1 and 4 will both be short, and they will be chemically unique. Carbon 2 has some symmetry, so it's tall, and carbon 3 has some symmetry, so it's also tall. So things to note from the carbon NMR. You should be able to uniquely distinguish a monosubstituted ring and a para-substituted ring. They should stand out. Ortho and meta, though, will look exactly the same by carbon NMR, but you could distinguish them if you had the IR and the proton NMR. But by carbon NMR, probably not able to distinguish one from the other. In terms of proton NMR, again, we are looking in this region of 6.5 to 8.5 parts per million. And there are going to be 3 different types of protons for a monosubstituted ring due to symmetry. So proton A should integrate for 2 protons, proton B should integrate for 2 protons, and proton C should integrate for 1 proton. And I put that information over here. Proton A, if you look at your neighbors, you only have 1 neighbor with a hydrogen buddy, so that's why it's a doublet. Proton B, if you look at your neighbors, they each have a proton, so you've got 2 proton neighbors, so it's going to be a triplet. And proton C has 2 proton neighbors on the adjacent carbon atoms, so it's also a triplet. Okay, ortho substituted, you have 4 chemically unique protons, and they should each integrate for 1 proton. Proton A, if you look at your neighbors, there's only 1 proton on an adjacent carbon, so it is a doublet. Proton B, you have 2 neighbors on the 2 adjacent carbons, so you should be a triplet. Proton C has 2 neighbors next door on the adjacent carbons, so it's also a triplet. And proton D, on the adjacent carbons, there's only 1 proton neighbor, so it's also a doublet. If you look at meta-substituted rings, you still have 4 chemically unique protons, and they each should integrate uniquely. Proton A, if you look at your neighbors, has only 1 proton neighbor on an adjacent carbon, so it's a doublet. Proton B, when you look at the neighbors, there are 2 neighbors next door, so it should be a triplet. And proton C, when you look at your neighbors, has 1 neighbor next door, so it should be a doublet. And proton D, when you look at your neighbors next door, don't have a proton buddy at all, so proton D is going to be a singlet. So if you couldn't distinguish ortho from meta by carbon NMR, you should be able to distinguish them by proton NMR. The multiplicities are very different for the peaks. If you're looking at para-substituted, there is again a plane of symmetry, so there's only 2 different types of chemically unique protons. HA will integrate for 2 protons, and HB will also integrate for 2 protons. When you look at HA, at the neighboring carbons, there's only 1 neighbor next door, and so the signal itself is a doublet. Proton B, when you look at your neighbors next door, has 1 neighbor, so it's also a doublet. You're going to get a doublet of doublets for a para-substituted ring. So I think that's really useful information to have in terms of these aromatic rings and being able to distinguish which substitution pattern you are dealing with at any given time. I thought it might help to look at individual spectra to compare these things. So we're going to go online and go to sigmaaldrich.com. This first spectrum that I have up is the spectra for bromobenzene. It's a monosubstituted aromatic ring. Now, for bromobenzene, maybe not the best example, but it is the example we have here. We have the carbon NMR up here. This is where we're looking at the carbon signals. And we have 1, 2, 3, 4. This one is the shortest one. This is the one that has the bromine attached to it. Typically, this medium-sized peak really is much taller. It's just not for this particular molecule. Oh, wait a minute. No wonder it's not tall. I'm looking at the wrong one. Sorry. This one's the monosubstituted. No wonder I'm like, that should be taller. Sorry. 4 peaks. This is bromobenzene. And the short one here is for the carbon attached to the bromine. Here's the medium-sized peak and then the 2 taller peaks. This is very typical for the carbon NMR. As we look at the proton NMR, they're usually very messy, but some things I'm noticing here is an integration line of 2 and then an integration line of 3. Those are not equivalent, but there are 5 protons. This one looks to be a doublet, and that is a mess that I can't decipher. But as I compare that to what we were expecting for a monosubstituted ring, we do have a doublet that integrated for 2 protons. The other problem is, though, you have 2 triplets on top of each other. Oops. All right. This one's the ortho substituted. I'm going to be much more careful now. With the ortho substituted, you have 2 short peaks, right here and right here. And this one, by the way, is ortho-bromotoluene. Another way of putting that is ortho-bromomethylbenzene, if that's helpful to give you an idea as to what the structure is. But these are the 2 short peaks. And then we have 1, 2, 3, and 4. Those 2 are actually together in here. But 1, 2, 3, and 4 tall peaks. And I know that's really hard to see. Down here in the Proton Nmr, if you look at things, we integrate for 1, 2, 3. I hope you can see that. So 1, 2, 3. There's 4 protons here. There are 2 signals on top of each other in this area, but I hope you can see the doublet and I hope you can see the triplet. So if we're looking at ortho substituted, we should see 2 doublets and 2 triplets. That's what we are expecting to be able to see. So we see one of the doublets and one of the triplets. What we have here, unfortunately, is a doublet, the 2 taller peaks on top of a triplet. So little, then it goes up to the smaller of the 2 tall ones, and then a little one. I know that's terrible, but that's oftentimes life. It's definitely not just one triplet. But that's an ortho substituted ring. Meta-substituted. So this is meta-bromotoluene or meta-bromomethylbenzene. We have 1, 2 short peaks and 4 tall peaks. So there's 6 chemically unique carbons, which is what we expect. We're thinking about meta-substitution. And in the Proton Nmr, we should expect a triplet, 2 doublets, and a singlet. If you look at your integrations, it's integrating for 2 to 2. It's 2 to 2. What we have in here is a mess. But you have a doublet in here on top of a doublet. So it's kind of ugly, but that's what we have, is a doublet on top of a doublet. There is a triplet that is underneath a singlet in this case. So I know that's ugly, but this is reality when you're looking at spectra, which is why you oftentimes want to look at more than one type of evidence to try to figure this out. They're often on top of each other. Okay, back to para for real. So para substituted ring, 2 shorts and 2 talls, which is what we are expecting from the carbon NMR. Proton NMR should have 2 signals, each of them integrating for 2, and each of them should be doublets, which is what we do see here. So this integrates for 2, this integrates for 2, and each signal by itself is a doublet. Just in case you're wondering, this little guy right here is from the solvent, so you would ignore that one. I hope that gives you half a clue as to where you should be looking, and the reality that spectra are oftentimes messier than what is predicted. But it gives us hopefully a guidepost for trying to figure out what it is we need to be looking at as we try to solve these problems.